Hi. So in the last video, we studied about the real numbers and theorems related to arithmetic, Euclid division theorem, and we also studied the application of theorem of arithmetic to prove that root 2, root 3 are irrational numbers and its application in finding LCM and SCF, etc. So, in this second section on real numbers, we are going to study their decimal expansion. So, if I start with a very simple fraction or rational number, so very simple fraction or rational number, which is just a minute, sorry. So, if I convert this fraction into decimal, I get zero point 0.5. Then if I divide or if I take the rational number 1 by 3 and if I divide, then what I get is 0.333, so on. Then I take the next fraction 1 by 4. So what will I get? I get 0.25. I take another fraction 1 is divided by 5. I get 0.2. Now I take another fraction 1, the same number. Now I divide by 6. I get 0.1666 and up to infinity. Now let us take one more fraction. 1, say we divide 1 by 7, or we take 1 by 7 as a fraction. So what we get? It is 0.14285714 dash 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 dash. What if we take one more fraction 1 by 8? So what is the result? So we get 1.125. Now let us not stop here and let us check some more fractions. 1 by 9. So the result is 0.1111 repeated n number of times. Let us take one more fraction 1 by 10. The result is 0.1. So what do you see in all these fractions? See, this is terminating. This is terminating. Here we have denominator 4. Here we have denominator 2. Then here we have denominator 5. So this is also terminating. So here we again have a terminating decimal and the denominator is 8. Now again we have terminating decimal and denominator is 10. So what we observe that whenever denominator contains factor of 2 like 2 or 4 or 8, then the fraction is terminating. Or if we have even 5 in the denominator or any combination of 2 and 5. So here we have 5. 5 that means 2 multiplied by 5. So from this simple exercise we can conclude that whenever so we understand from this exercise that whenever we have 2 or 5 or any factor multiple of 2 or 5 or of both, then the fraction is terminating. Fraction, or we can say the rational number, is terminating. Otherwise, it is non-terminating. So if we have 3, 7 or any prime number or any multiple of 3, any multiple of any other prime number, then the rational number will be non-terminating. So this takes us to the next theorem, which states that if say x is a rational number, so we can express it in the form of p by q. So we can express this rational number in the form of p by q, and if prime factor of q are equal to 2 to the power n into 5 to the power m. So where n and m are positive integers. Positive integers. So in this case, decimal expansion of x, that is p by q, will be terminating. So you can say that decimal expression of x, that is p by q, will be terminating. In simple words, so whenever denominator contains factor of 2, or sorry, multiple of 2 or multiple of 5 or multiple of both, then the decimal expression of that rational number will be terminating. In other words, if it is not a multiple of 2 or multiple of 5 or multiple of both, then the decimal expression will be non-terminating. So we have now another theorem which states that if x is a rational number and so it can be put in it in the form of p by q, and prime factor of q are not equal to 2 to the power n or 5 to the power n. That means q is not q does not have a factor 2 or 5 or any of their multiples. Then the rational number is non. So if q is not equal to 1, that means q doesn't have 2 or 5 as a factor, then the decimal expression will be of that rational number will be non-terminating. So takes the exercise that we have done, in which we found out the decimal expression of various fractions or rational number. So from this observation, we have come to two theorems, theorem 1.6 and theorem 1.7. Now we have one more theorem to cover. So this theorem states that if say x be a rational number, so if it is a rational number, then we can express it in the form of p by q. So x equals to p by q, and p and q, as we know from the definition of rational number, are integers. Here we take positive integers. And if x, the decimal expression of x, if decimal expression of x is terminating, so if we divide p by q, then we get a decimal which is terminating. Then this theorem states that in that case q will have 2 and 5 as the factor. So q can be expressed in the form of 2 in the form of 2 to the power n or 5 to the power n. So where n and m are positive integers. So in simple words, if you see what this theorem states, that if there is any rational number and if its decimal expression is terminating, then the denominator that is q in the of that rational number, now will have 2 and 5, only 2 and 5 as their factor. 2 and 5, either 2, either 5, or 2 and 5 both. So the decimal expression can be terminating only if we find that there is any rational number and where the denominator q contains 2 and 5 as the only factor. So the how we can see now that these theorems can help us to find out whether any rational number will be, the decimal expression of it will be terminating or will be non-terminating. So what we need to do is we need to simply look at the denominator, that is q, and find out whether the factors of q contains only 2 or 5 or both, then it is terminating. If it contains any other factor besides 2 and 5, then the decimal expression will be non-terminating. So this completes the section second of real number.